You write code. You test it. It runs fast, right? You click, it responds. Your users are happy. But here's a shocking truth, that fast code you just shipped? It might actually be brutally, inefficiently, catastrophically slow when it matters most. We often think about speed in terms of processor clock cycles, or how much RAM we have. We upgrade our machines, or we pick a supposedly faster programming language. But that's like trying to make your car go faster by just painting it red. It might feel quicker, but under the hood, nothing has changed. So, what's the real secret to software speed? How do we build systems that don't just feel fast on a small scale, but truly are fast, even when they're handling millions of users or gigabytes of data? Let's unlock the fundamental principle that separates truly fast software from the imposters. And here's where it gets interesting. The real secret to software speed isn't in your hardware. It's in something far more fundamental, the algorithmic complexity of your code. Think of it like this: imagine you're a chef, and you need to slice 1,000 vegetables. You could pick up a tiny paring knife and start slicing them one by one. Or, you could use a high-speed food processor. Both methods will get the job done, but one is dramatically more efficient, especially when the workload grows. Algorithmic complexity is a way for us to measure how much time or memory an algorithm will take to complete, as the size of its input grows. It's not about exact seconds or milliseconds, because those can change based on the machine. Instead, it's about the rate at which performance degrades, or improves, with more data. This is crucial because it helps us predict how our software will behave when it goes from handling 10 users to 10 million users, or 10 records to 10 billion records. Understanding this concept is like having a crystal ball for your code's performance. It allows us to build systems that scale gracefully, rather than collapsing under the weight of real-world demand. Without it, we're just guessing, hoping for the best, and often ending up with slow, frustrated users. Complexity. But the genius part is this: we use a special kind of shorthand to describe this complexity, called big O notation. Don't let the name scare you. It's actually quite intuitive. Big O gives us a way to describe the upper bound of an algorithm's growth rate. It simplifies things, focusing on the worst-case scenario and ignoring constants or smaller terms that don't matter when the input becomes truly massive. Let's look at a simple example: finding an item in a list. If you have a list of 10 items, and you need to check each one until you find what you're looking for, at worst, you might have to check all 10. If the list grows to 1,000 items, you might have to check 1,000. The work you do scales directly with the number of items in the list. We call this linear time complexity, or O(n). The n here represents the size of our input, the number of items in the list. If you double the size of the list, you roughly double the work. This is like searching for a specific book on a shelf by checking each one from left to right. The more books there are, the longer it takes. Let's dive a bit deeper into the spectrum of complexities. It's not just O(n). We have an entire range, from the superfast to the unbelievably slow. Understanding these categories is like knowing the difference between a bicycle and a rocket ship for getting around. First up, we have O(1), or constant time. This is the holy grail. It means no matter how big your input gets, the time it takes stays the same. Think of it like grabbing a specific playing card from a deck after someone tells you its exact position. You don't need to look at every other card. It's instant. Then there's log(n), or logarithmic time. This is incredibly efficient for large datasets. Imagine finding a name in a dictionary. You don't check every page. You open to the middle, decide if your name is before or after, then repeat the process on half the remaining pages. You rapidly narrow down the search space. Next, we already saw O(n), linear time. Good, but not great for massive datasets. Then we have O(n) log(n), which is typically where efficient sorting algorithms live. It's a bit more work than O(n), but still very manageable for huge inputs. And finally, we hit the danger zones. O(n)², or quadratic time. This means if you double your input, the work quadruples. If you have 10 friends, checking every possible pair is easy. With 1,000 friends, it's 1,000,000 checks. With 1,000,000 friends, it's 1,000,000,000,000 checks. This rapidly becomes unusable. Anything worse, like 2 to the power of n, exponential, or n factorial, is usually reserved for tiny, niche problems because they explode in complexity almost instantly. Here's the critical part. Why does any of this matter to us, the developers of modern applications? Because the scale of data we handle today is just mind-boggling. Your small, fast script handling 10 entries might become a performance nightmare when it hits a production database with millions, or even billions, of records. Let's put some numbers to it. Imagine an operation that takes 1 unit of time. If your algorithm is n, and you have 1,000 items, it takes 1,000 units. If it's n squared, that same 1,000 items takes 1,000,000 units. Now, bump that up to 1,000,000 items. n takes 1,000,000 units. n squared takes 1,000,000,000,000 units. That's a difference between a few seconds and thousands of years. This is why understanding algorithmic complexity is non-negotiable. It's the difference between an application that flies and one that grinds to a halt. When you see cloud VM benchmarks, often the biggest performance gains don't come from faster processors, but from optimizing the underlying algorithms. Even with amazing advancements like WebAssembly, WASM, which lets you run near-native performance code in the browser, if your big O is bad, it's still going to be slow when faced with large inputs. We need to be smart about how our code scales, not just how fast it runs once. So, where do we see this playing out in the real world? Everywhere. Think about an online store. When you search for a product, if their search algorithm is n, and they have millions of products, that search would take forever. But with efficient log n search techniques, like those using indexed data structures, it's practically instant. Consider your social media feed. Every time you scroll, the system is sorting and filtering thousands of posts, trying to show you the most relevant ones. If that algorithm were n squared, your phone would catch fire trying to process it. Efficient sorting algorithms, often n log n, make this possible without you even noticing the incredible amount of work happening behind the scenes. Another common trap is the n+1 query problem in web development. This happens when you retrieve a list of items, then for each item, you make another separate database call. If you have n items, that's n+1 database queries. If n is 100, it's 101 queries. This quickly turns an O1, or O log n, database read into an n operation, hammering your database and slowing down your application to a crawl. Understanding complexity helps us identify and fix these hidden performance killers. We've broken down the real secret to software speed, and it boils down to algorithmic complexity, expressed through big O notation. It's not about making your code run a few milliseconds faster on your laptop. It's about designing code that scales elegantly, performing consistently well no matter how much data or how many users you throw at it. So, how do we apply this? First, always think about the big O of your approach before you even write a single line of code. Are you iterating over a list multiple times within another loop? That's likely n squared. Can you use a hash map for constant time lookups instead of searching a list? That's an O1 win. Second, understand your data structures. Choosing the right data structure, like an array, a linked list, a hash table, or a tree, has a huge impact on the underlying complexity of your operations. A well-chosen data structure can transform an n search into an O1. Finally, always test your code with scaled data. Don't just verify functionality with 10 items. Throw 1,000, 10,000, or even 1,000,000 items at it, and see how it performs. That's where the true bottlenecks reveal themselves. It's a balance though. Sometimes, for very small datasets, a simpler, less optimized algorithm is perfectly fine and easier to read. Don't over-optimize for problems you don't have. This isn't just theory, it's a superpower for building robust, high-performance systems. Master algorithmic complexity, and you'll master true software speed. equals 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 equals. Final segment, close and summary, 1630 to 1700 hours. Equals 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 equals. We've peeled back the layers today, revealing that the true secret to software speed lies not in faster machines, but in smarter algorithms and data structures. It's about understanding how your code behaves as the world throws more and more at it. This foundation is crucial for any developer aiming to build something truly impactful. If you enjoyed this deep dive into algorithmic complexity, you're going to love what's next. In our next episode, we'll see how sorting algorithms use this secret to organize your data with incredible efficiency. Make sure you're subscribed so you don't miss it.